All right, exam 5 starts with section 11.6 and goes all the way up to section 13.1. We're not covering parabolas in section 13.1, but the rest of 13.1, the stuff with circles, is on it. So 11.6 to 13.1. Let's discuss a few things in each section that I kind of expect from you. Starting with section 11.6. 11.6 worked with the properties of logarithms. So let's find our way back to there and see what those are all about. That was your product rule, your quotient rule, your power rule, etc. So problems like number 61 would be an example of that kind of stuff. So let me zoom in a little bit here. And the nice thing about me zooming in with my book is that the answers are here if you wanted to take a look back at this. So it's a log base 2 of a couple things. Really, you've got a quotient and a product. So what you would do first is you expand it using the quotient rule. It would be the log of the numerator minus the log of the denominator. Then looking at the log of the numerator, you could use your product rule. Log of 2 times this root becomes log of 2 plus the log of the root. The last thing in here, it's kind of hidden. When you expand it, you'll end up with log base 2 of 2 plus log base 2 of x to the 1/3 minus log base 2 of y. The last thing in here that's kind of hidden is this part right here. Log base 2 of 2. What's that going to equal? Nope. 1. When you're dealing with the logs, you're asking yourself, what power of 2 gives me 2? And that answer is 1. The 1/3 comes out in front. 1/3 log base 2 of x minus log base 2 of y. So, yay. A couple other ones that you might look out for from this section as well. Problems like 24 and 26. Now these are some special properties of logs that are kind of useful when you run into them. Let's start with problem number 24. You've got the log base 8, 8 to the log base 8 of 10. The logarithm and the exponential function are opposite of each other. When you do the log 8 to the log base 8 of 10, those two operations cancel each other out. You just get the exponent. In the reverse order, but the same kind of principle, the log base 4 of 4 to the second power, again, those two operations cancel each other out. You're going to end up with the 2. There's one last example like that down here. 5 to the log base 5 of 8. Those operations cancel, you're just going to get 8. So, a couple problems like that. Problems like number 77, where you end up using these properties in reverse. There was a great example of one of these things that we did in reverse. Does anyone remember it? When we started pulling all these things together and got one big logarithmic term? Oh, I'm wounded. My log cabin joke didn't stick with you? Oh, so shameful. Okay, so you would bring these two together as the log of x times x plus 2. That's using your product rule in reverse. Log base 3 of x times x plus 2. And then you'd pair it up with this last term here. You'd have the log of that product divided by 8. So you get something like this over here. Oops, sorry. Let me zoom out a little bit. There you go. So the first two terms come together as a product. The next one comes together as a quotient. And if you have specific questions about that, come see me afterwards. I got to get you out of here quickly, so I am going to go kind of quickly, but get some help on these things if you need them. We had a change of base formula for logarithms. I will give you the change of base formula. Change of base formula looks like this. Log base a of x. You can calculate that as the log of x divided by the log of a. A is some base that you can't calculate directly, so there's this change of base formula. You'll not be required to use this on every single problem that you face on the exam. So that's 11.6. Let's move on and take a look at 11.7. There's a lot of stuff there that we covered. If you remember, we spent an entire day on that one section. In fact, some of the problems that I think I gave you a whole list of problems to work in class that day, didn't I? All right. Those problems happen to be highlighted in my book. They'd be good to know. They're examples of all the different kinds of things that we did. Problems like 31. So this is an exponential equation. One way you can solve exponential equations is by taking the logarithm on both sides. And when you do, you'll end up with this expression and something like that. You know, I could ask for either one. Okay? You should be prepared to give me the decimal values. You might want to practice this kind of a calculation. Problem 39 is similar in as much as it's an exponential equation. You'd probably want to start by taking the log base e on both sides. Now, what's the notation for log base e? ln. So if I take the ln on both sides, then on the left-hand side, I'll just end up with the exponent, negative 0.02, excuse me, negative 0.2t, and then divide by that negative 0.2 and finish solving here. So a quick solution. ln. Yeah. Yeah, in class what I did was I would write it, instead of taking ln of both sides, ln of e to the negative 0.2t equals ln of 14.2. So instead of doing that, I did log base e, because in my mind it's easier to see that the left-hand side simplifies very nicely. These two cancel each other out, much like problems like 24 and 26 did from the previous section. You get negative 0.2, and now I'll just go back and call that ln. What else? So 31, 39. 43 is a little bit different. Actually, a lot different. 43 is a logarithm problem. Now, there was two methods by which we would solve logarithms. Since I don't have the log of something equals the log of something else, the way I solved this one was to rewrite it using exponents. What base is understood to be here with the log? 10. So 10 to the second power equals 7 minus x. You can go through and solve there and you'll end up with negative 93. You rewrite it using exponents. 10 to the second power equals this term right there. Let's keep going. 55. 55 is yet another one that you would solve the same way. You can't solve this by canceling logs or anything fancy like that because I don't have logs on both sides. Instead, what you would do is bring these two terms together as the log base 5 of 4x minus 1 times x, and then rewrite it. So after you bring it together using your properties of logs, your product rule, then you can get rid of the logs. But you're going to get rid of it by rewriting it. The nice one that we worked on in this section was when you could just say, oh, well, I have the log of something equals the log of something else. Stuff like problem number 61, for instance. Let me see if I can get, there we go. Since I have the log of something equals the log of something else, effectively I can get rid of the logs. And I can look at 2x equals 4 and solve that way. I can't do that for a problem like 63 because I don't have logs on both sides. So here I'd have to rewrite it using exponents. We did 65 in class. That's a good one. Another one with exponents. Let's see. 81. I think that's another one that we did in class. For 81, you could bring the 2 up here, make that log base 2 of x squared, move this to the left-hand side, then bring them all together. You're eventually going to have to rewrite it as a quadratic equation. You'll end up with a repeated solution of 4. Yay. I hope you enjoyed section 11.7. Oh, we also did some radiocarbon dating problems. On the exam, I would give you the formula that we derived. And I think that formula, if I remember right, was A equals A sub 0 e to the negative 0.000121 t. So that's what you would use for your radiocarbon dating problems. But I will give you that part. Chapter 12. This is going to start going faster. Section 12.1. The point of this section was to remind you how to find solutions to systems of equations. We went over a couple different methods. We went over the addition method, substitution method. But one thing I don't want you to forget is kind of what it all means. When you find the solution to a system of equations, you're looking for a special kind of point. Can anyone tell me, without even reading the problem or doing the problem, what the solution is to this system of equations? Yeah, about 140 and 350, right? Don't forget that your solution is the point where these things cross each other. So geometrically, I want you to know that. Now, we did some by addition, we did some by substitution, know those. One thing to keep in mind is that not everything solves. You are going to run into equations like number 51 where things don't solve. In this case, it's because the two lines are parallel. And if you played with this, you might be able to see that. You can determine that using Cramer's rule. You show that the determinant is 0, determine matrix of coefficients, so that either it's inconsistent or dependent. You have to play with it from there. Section 12.2, I'll probably ask you to solve one of these things by hand. So I'd be looking at problems that work out nicely. I'm not going to give you something that's going to work out too crazily. So, good examples of some problems that work out nicely are like 15 through 21, that kind of thing. There's plenty of examples on this page in the homework that will work out pretty nicely. Section 12.3, I did a couple application problems. I showed you how to set up the system of equations for that nutritional problem. I also showed you how to set up the system of equations for curve fitting, figuring out this one. So I didn't ask a whole lot of you. I only gave you a handful of problems in this section, and I'm going to pull the problems from this section from the homework. Solving with matrices. That's a cool trick. I expect you to be able to solve with matrices. Something like problem 47. We did a couple like this in class. That's pretty nice. Nice trick to be able to solve them with matrices. Cramer's rule, this section, 12.5. Probably ask you to calculate a 2 by 2 and a 3 by 3 determinant. What I might do is make calculating a 3 by 3 determinant part of a Cramer's rule problem, where I ask you to solve a system of equations by Cramer's rule. So what I'd do to make that reasonable is I would probably give you 3 out of the 4 values. In calculating Cramer's rule, you need d, dx, dy, and dz. In the 3 by 3 case, I'd probably give you 3 out of the 4. I want you to calculate the 4th one and use it to finish solving by Cramer's rule. Finally, section 13.1. There were several things we did with the graphs and equations of circles. We started out with an equation and we came up with the center and radius. Now let's just take a look at problem number 19 here, kind of on the quick. So x plus 3 squared plus y minus 1 squared. Man, it's just a bad screen day. All right, thank you. Equals, where was it? 16? You know what? Just for my convenience, I'm going to make that 4. So this is problem 19-ish. What's the center of this circle? Good. -3 and 1, and the radius is 2. So what would the graph of this thing look like? How would you graph that? Well, it's a good question. So let me draw a quick graph here for us. And we'll label it with some points. I would give you the graph, but yeah, I would expect you to be able to graph it. So 1, 2, 3, that should be good enough. 1, 2, 3. But yeah, I will give you a graph, and just kind of a hint. If your graph doesn't fit on what I provide, one of us made a mistake. And I'll let you decide who you think that is. Okay, so -3, 1, 2, 3, and 1 is our center. And when you're graphing these things, what I would suggest is that you plot what I call the points of the compass. I'll move to the east 2, to the west 2, north 2, and south 2. So that kind of frames your circle. And then as best you can, try and draw a smooth circle through those points. And I'll make you a deal. You don't laugh at mine, and I won't laugh at yours. Good enough. Okay. See ya. I don't